Okay, we are very sharp on the schedule. Thank you very much, Franz and Markus and Hans, for organizing this workshop. I'm trying to get a little bit of understanding about quantum harmonic analysis, and I find it really fascinating. My talk only has to do maybe with harmonic analysis, frames. So I like to present this here because it is based on a paper by Charlie. And so we got into this because of that paper. So it's a work in collaboration. You see, well, Carlos just talked, and Felipe is the same guy who was collaborating with Carlos. So he is a postdoc at our department, and so we had this work. And I hope this is readable. In order to get this background, I took a picture of the ESI blackboard and put it as a background. Can you read it? And then I wrote with chalk on the tablet, of course, right? Okay, so the idea is to talk about frames and reconstruction of signals. So we are always going to be in a separable complex Hilbert space. And we have two sets of frames indexed by the same index set. And we say that phi and psi are woven if they're for any subset of the index set. If I take the elements of the first frame in the sigma, which is the subset of the index set, and the elements of the other frame in the complement, and that should also be a frame. If that happens for any subset, then we call these two frames woven. So this is the definition. Clearly, you can talk about many woven frames, like the picture. There were many colors which were all woven into each other. And where does this come from? Well, the idea is related maybe to what Carlos said, that you wanted to measure, you couldn't measure a signal, but you could measure in different time. Well, here, instead of measuring the signal only with one set of sensors, sometimes one sensor gets activated and sometimes another one. So you are interested that any combination of activation will work and you still can get the whole information. So this is the motivation for studying when two frames are woven. The first this is what I just say. I give an example just to get into the motivation. This will be an example later. So if I take the exponential functions where I denote by, well, I think this pointer doesn't work. With E sub alpha omega is just the exponential in omega alpha. And I take two sets of exponentials indexed by alpha k and beta k. And we assume that for both, they are frames for the Paley-Wiener space of length 1, so Paley-Wiener 1/2. Then we will say that they are woven. Well, if they are woven, then for any f, we can either use the samples at alpha k for f or at beta k, and in any combination, how I like. This is what makes this set useful, because sometimes you don't have the information on all the integers, but maybe you have on integers and something else, and if they were woven, you could still recover it. And now comes the side this is the paper, which is where it first was addressed. It's by Bemrose, Casassa, Charlie, Lammers, and Lynch. So when I have a long citation, this is this paper. And they have very interesting results. Many of the things are interesting, but the ones I will use is if two frames are woven, then all the weavings, I mean all the possible combinations, have uniform frame bounds. So they have all the same. Also, if I have two Riesz spaces are bases which also generate, so they are also frames. I can ask whether two Riesz spaces are woven. And it's true that if the frames, they are woven as frames, they will also be Riesz spaces. All weavings will be Riesz spaces. And with the same constant. And if we have a bounded invertible operator, if phi and psi are woven, T of phi and T of psi are woven. This will be useful later for some calculations. First, I want to show some easy example which show that the problem is not so easy. I start with a finite-dimensional case, set of generators in Rn or Cn, wherever you want. For example, take any orthogonal basis and permute two elements. V1, V2, V3 orthogonal, V2, V1, V3 orthogonal. Are they woven? Never. So what happens? The problem is being woven is strongly dependent on permutation. So if I permute the elements, they may not be woven anymore. So we will consider woven frames up to permutation. So the question is, does there exist a permutation of one of them or of the two? Because if there is of one, then you can apply them to both, such that the frames then become woven. You may think this is trivial, that this always will happen. No. Take V1, V2, V3, an orthonormal basis, V2, V1, V3, they are woven up to permutation. I go back and they are woven. However, E1, E2, E3, E1 plus E2, E2 plus E3, E1 plus E2 plus E3, you can permute them as many times as you want, and they will never be woven. So some are and some not. Okay, so this is the question. So the question is, can we see when two frames are woven abstractly? There are conditions which we found in this case. Just in the finite dimensional case, we start and we look at two frames, at two sets of generators, and we try to see if we can characterize which condition they have to satisfy in order that they are woven. And so if we look at this example, you can always take a set of generators and permute them in such a way such that the first n are a basis. I have m. If m is bigger or equal than n, then you can take the first as a basis. And the other one also. So if these two permutations give rise to woven bases, then the frames V1, Vm, and W with the two permutations, I put them together, are woven frames. So if I have two generators, I permute them until both have the basis in the beginning, a basis in their beginning, a basis. If this basis is woven, then the frames will be woven, up to permutation, of course, right? So the guys that are woven is the V1, Vm, and the W permuted one permutation of M. Yes? So this is not the original ones, maybe, but up to permutations, they are woven. The question is that converse true? We don't know. So we don't know. In this talk, there will be many things we don't know. I'm not going to talk about only things we know, but there are many things we don't know, even very simple questions like this. The concrete question is, given two finite woven frames, does there exist a permutation of one of them that yields aligned woven bases, aligned in the same position? We had some communication with Maria Lukakis, who worked on some similar problem, and she thought she had an answer to this, but she missed the permutation part. So she came up with an example that had no aligned basis, but not up to permutation. So once you permuted them, we had the frames. But well, we don't know the answer to this. Would be interesting. So we consider, or we look at the problem if we can characterize when two bases are woven. And this we could do. So if I have a matrix, an n by n matrix, I'm going to look at two frames of n elements because I want them to be bases now if they are woven. I call the central submatrices of a square matrix the matrix which are central submatrices, central subsquare matrices. So you denote them with AJK, with JK and J. And J is just any subset of that. It already hints that we are in some setting similar to before. So we have to do the n-1 central matrix. So now we want to see when V1, Vn and W1, Wn are woven. So I look at the change of basis matrix. So with this notation, we write each W as a classical AJI, Vj. And so A is the change of basis matrix. And when will these two frames be woven? So the theorem we have is that they are woven if and only if all central submatrices of A are inverted. So it reduces to check 2 to the n-1 determinant. Hans knows that it is not easy, but you have to do determinant. Since the organizers allowed me a little bit more of time, I wanted to show just a little bit of a proof here. Usually I don't do proofs in the talk, but today, since this is easy, I can do it. So if we take the mapping that sends each basis V to EJ and well, I have it. If we take the mapping, I think I mixed here something up. If I take the mapping T that sends Vj to Ej, this makes that T of Wi will go to the column I of the matrix, of the change of matrix. Sorry, I had it here. This is the change of matrix, yes? So the matrix T sends Vj to Ej, and therefore T of Vi is the ith column. And by the theorem of the paper I cited, these two bases are woven if and only if E1, En and A1, An are woven. So I have just to compare the orthonormal basis, any orthonormal basis, with the columns of the change of basis matrix. Well, but when are these woven? If this is a basis for any subset J of 1n, right? I take the elements of EI, the orthonormal, the J orthogonal vectors, EI, and then in the complement, the columns of A. So I have identities, the EI vectors all spread out in my matrix. Well, and then this means that when I take the matrix A sub J, which is just replacing the columns of A with the canonical vectors, I say canonical, but it's the orthogonal vectors, right? So I need that this matrix is invertible in order that this is a basis, right? So having that these vectors are a basis, I have n of them. The matrix that, if I put them all in columns, has to be invertible. But this matrix, if you calculate the determinant using expansion exactly on the elements of the orthogonal basis where the ones are, is exactly a central submatrix of the original matrix A. It's simply by calculating the determinant. So we have the theorem which gives us a characterization in terms of matrices of when two bases are woven. So what do? Since we didn't go very far, we just have a little more knowledge. We know that two bases are woven if and only if all the central submatrices of the change of basis matrix are woven. Then I define a class which are all the square matrices such that all square submatrices, central square submatrices are woven. And if I add a little n, then they are of dimension n. I say woven when I say invertible, but I think it's... So by the previous proof, we know that if A is in Wn and A1, An are the columns of A, then if A is in Wn, the columns of A and the orthogonal basis are woven. This is because all square matrices, central subsquare matrices, which will come out if you replace some columns with some of the 0, 0, 1 vectors, these are all invertible if they are woven. So why is it useful to have woven? Because we already saw it early. Well, if we have two woven bases, then we can recover if A is a matrix whose columns are woven, and I have a vector x in Cn, I can recover it if I know the coordinates in some set and the multiplication of the vector with the matrix in another set. This is also somehow related to dynamical sampling. So you don't know all the coordinates, but you know the coordinates in a set, and you know the coordinates in a subset, in the complement. And in that case, you have perfect reconstruction. Or on the other hand, we have that if A is satisfied that all the matrices, if you replace the columns by canonical vectors, are invertible, then A will also be in the set Wn. So we looked at W or Wn. How big is it? Well, it's very big. Has Lebesgue measure, the complement has Lebesgue measure 0, much more. Wn is an open dense set in the Zariski topology because it is the inverse image of 0, where the pi map is just the product of the determinants of the square central submatrices. So this is a very, very small set. However, it's not very easy to identify elements in it. For example, well, obviously 0 cannot be in Wn because it's not invertible. But for example, if you have a matrix in A and you square it, just the matrix and itself. In this example, this guy, A, is obviously in W2 because the only square submatrices are 2, 1 and 1. So the whole matrix and the 1 and the 1. So it's in W2, but the square, which is this one there, so the matrix is invertible, but the central submatrices are not. Okay, so it's not closed under multiplication. Obviously not under addition. This is easy because you just take one matrix and subtract the same, so it's not closed under However, it does satisfy many things. So it is invertible. It is in W. I forgot to put the subscript, but it's Wn. You always take one fixed n, if and only if it's invertible, and A to the minus 1 is also in W. Also, if A is in W, then the transpose or the conjugate will also be in W. This is not surprising. The next one is a little bit more. So if I have A in Wn and take B either a diagonal invertible or a permutation matrix, and I conjugate A with B, this will be in Wn. If A is symmetric and either positive definite or negative definite, then A is also in W. This is easy. If it's lower or upper triangular and invertible, then it's also, these are sort of the trivial examples. This is almost all we can come up with. And if A is in W and B is a central submatrix of A, then B is also in W. This translates from one. Well, here comes the first thing. The 3. Is it true that if B star AB is in Wn, then for all A in Wn, is it then true that B is either diagonal, invertible, or a permutation? Our guess was that if B was unitary, it should work, but it doesn't. The example is a little bit cumbersome, that's why I didn't put it. But it's not true that if B is unitary, then it will take all the matrices from Wn into Wn. So it's diagonal invertible or permutation. And arbitrary unitary doesn't work. I think I didn't put the example. Moreover, if I permute rows or columns of the matrix, this may take me out of W. So in order for being able to remain in W, all minors of A have to be non-zero. Not just the square central submatrices, but all square submatrices. If we want that any permutation or dilation or of rows or is closed under, if we want that A with a permutation of rows or of columns belongs to W, then I need that all the minors of A have to be different from 0. Well, somebody has an idea where I'm heading. The first matrices that come into mind are the Fourier matrices. Because we know from Chebotarev's theorem that if P with N is prime, then all the minors are invertible. So it is true that any square matrix of a Fourier matrix Fn, so Fn is just to put the discrete Fourier transform as columns, or rows, however you like to think it. This is the matrix, the Fourier matrix N. So when we saw, we said, can we extend it? There may be another matrix because we don't need that all minors are invertible. We just want the central matrices to be invertible. And so, well, the order is a little bit different, but I put it because it's nice. If N is P times R, with some conditions on P and R, which I'm not going to say here, then Fn belongs to Wn. Okay, so this Maria Loukakis proved after seeing our paper. She found this as a generalization of Chebotarev. We think that the conditions on P and R, she believes that the conditions on P and R can be weakened, but for now they are related somehow. What we did before was if we have an n bigger or equal than 2, then all central 2 by 2 matrices of Fn are invertible if and only if n is square free. So 4 doesn't work. F4 doesn't work. F6, probably yes. We believe it satisfies this condition, but I'm not now. Yesterday in the talk of, I'm mixing the David or Philip? David. He talked about 6 as a difficult case, so no, I'm not there to say if it's true or false, but I believe 6 works. As a conclusion of this is that we can prove that if, in order that Fn is in W, we need that n is square free. So we know that if you have a square for any P, a square in your expansion, in the prime number expansion of n, if you have a square, it doesn't work. And this is easy in some sense to see because then if you have a square, then you can find a 2 by 2 submatrix where the ones are in the diagonal. Somewhere they are in the diagonal, and then this little submatrix is not inverted. We don't know the reverse. We tried very hard. Mihalis Kountsakis made a program to see if this is true. We don't know. We conjecture that it is true. And when we conjecture that n is square free, then Fn is in W. We had a deadline for the paper, so we sent it with the conjecture. We couldn't prove it. And then, much later, the group of Götz-Pfander, independently, they didn't know our paper, it was not published, it was in the archive, but they also conjectured the same thing, that if n is square free, then the principal minors of the diagonal of Fn are in W, and they come from a completely different, because they are trying to find exponential bases. And so of intervals so they were looking for that, and they were working with Fourier matrices, and so they came up with the same thing, and it's in the archive. So I later give you the correct reference. But we don't know. We have no answer to this. The interesting thing is that if Fn is in Wn, then you can recover any vector x in Cn either by knowing its coordinates or knowing the Fourier transform of some coordinates. So you just know the first three Fourier coefficients of x and the last n-3 vectors, and you can recover x completely. This is because of the property of being woven. I guess this is why one is maybe interested when Fn is in Wn. So that makes me leave the finite dimensional case, and I go to the infinite dimensional case. Now we work in a separable Hilbert space. And again, I will talk about Riesz spaces. And again, as before, we say the two Riesz spaces are woven if any weaving of them yields a Riesz spaces. And now look at this following diagram. You can identify any Riesz spaces in H with the canonical matrix, canonical basis in L2 of I. You look at the operator, which takes L2 of I into L2 of I, and using these maps which go from H to L2, sending the Riesz spaces V into the canonical in I, and the Riesz spaces W into the canonical in I. And if A transpose is this operator here, it's just an infinite matrix, infinite dimensional matrix, well, we get the same theorem. So let us take any subset of I and define the square central submatrices as the matrices A, I, J, where I and J are in big J. Then, if we have two Riesz spaces of H, then I have the theorem which we had before. They are woven if and only if all central submatrices of A define uniformly bounded invertible operators. And this word uniform is important. So we need the same constant for all, but in other words, in some sense, in the paper in the original paper, it was already proven that if you have a Riesz basis which is woven, all the submatrices have the same, all the weavings have the same Riesz bounds. And here this is the same. The proof is essentially the same. You're again, instead of proving that the determinant is different from 0, you prove that it's an invertible operator in the same way than before. And so we call that the matrix A itself is a woven matrix. It comes out of the so if so I mixed a little bit the notation, I'm sorry, the matrix T is woven respect to an orthonormal basis if the associated matrix A is woven. I mean, here T of Vi is the sum of Aj. So now I just used as one of my woven matrices, of my Riesz basis and orthonormal basis. And so we define the operator or the bounded operator to be woven if this happens. And then we have the same theorem. And so T is woven if and only if every vector of F. This is the same theorem I had for Cn. We have it here in infinite dimension. That every vector of F can be recovered from the projection of F, the projection onto the subspace generated by J in the J first coordinates of F, or I divide my space into the coordinates of F in my orthogonal basis, which are in J, and the complement are T of F. So I check the coefficients of F in my in some examples, in some elements, and the coefficients of T of F in some examples. And this allows me to recover F if T is woven. So we had a theorem that T is woven if and only if every vector of F can be recovered from PJF union PJ complement TF. I think the notation is a little bit cumbersome, but it means that you project onto this set of the vectors in J, where J is the index. So this is makes it complicated. And I just put in this example because this theorem gives a little bit more than the one they had in their paper, because they had a sufficient condition, and this matrix was not allowable under their condition, because there was a condition which was not necessary. And so, but with the necessary and sufficient condition, we could improve a tiny little bit the result about infinite dimensional woven frames. And we concentrated on the particular case of shift invariant spaces. Many of you are probably familiar. Shift invariant spaces are just spaces where any F belongs, then any translate of F also belongs to the same space. And now I want to see when two bases of S of phi are woven. So I take assume that the shift invariant space is generated by a single function. And I take all its translate and assume that this is a Riesz basis. And then I look at the perturbation results, which we all know. And so I take a function psi, which is also in the same space, that satisfies that the absolute value of the distance between phi and psi for all omega are less or equal than mu, okay? And if mu is less than a or a over 2, now I'm not sure, but I think with a is enough, then not only t, k, and phi are Riesz spaces, which we knew by the perturbation result, but they are also woven. So you can replace any subset. So you can take some translates from phi and some translates from psi. This is interesting because sometimes you have access to some function better than to others. And so you can replace any translate from phi with any translate from psi. And these will be woven. And this is just because of the perturbation result of Kavek. No, it's not Kavek, but something similar. So I guess this was all I wanted to say. These are the references. Our paper was in a volume dedicated to Charlie. And these are the two papers of the group of Götz Pfander. And thank you very much for your attention.